and thank you for jumping into the second part of my talk on ambient obstruction solitons and homogeneous gradient box solitons. So in part one, we talked about general geometric flows, defined a lot of the terms that we're using. For this part of the video, I will assume that you have watched part one. We will use one of the lemmas that we went through in part one. So if you haven't watched part one, pause, go back and watch through that, or at least click through it. And then you can jump in that part two. So for part two, we are going to be focusing on defining the ambient obstruction tensor, looking at the ambient obstruction flow, what on earth are ambient obstruction solitons, and finally we'll look at some of the new results that I found and talk a bit about the methodology for finding these results. So the ambient obstruction tensor is defined to be this tensor given by script O, and it's defined as the obstruction to an n manifold having a formal power series solution for a Poincare metric in dimension n+1. Okay, a couple important things to point out here. One, the ambient obstruction tensor is only defined for even n greater than or equal to 4. So it is not going to give us a nice exhaustive dimensionality, but it does work for even dimensions. And it's defined as the obstruction to a manifold having a formal power series. That's all fine and good, but why do we care? Okay, so the thing that I think is most intriguing about the ambient obstruction tensor is its realization as the gradient of the Q energy. Okay, so looking at Branson's Q curvature, we can look at this Q energy as the integral of Q dVg. And there are a lot of different types of energies. We'll talk about the Weyl energy in part 3. Okay, but we have this energy, and if the ambient obstruction tensor is going to be the gradient of that energy, or think of it loosely as the derivative of that energy, well, how do derivatives relate to things? We know that when the derivative equals 0, for a curve, for example, or a surface, when the derivative equals 0, we have an extrema, right? Or a flattening out, if you will. It's not always an extrema, but what this means is that since O is equal to, let's call it F prime, loosely again, this means that where O equals 0 is a critical point of some Q energy. Okay, now, again, putting this very broadly, critical points are cool or interesting. They almost always indicate something that is going to be useful to us in the long term. So considering a tensor like the ambient obstruction tensor and realizing that this tensor, when something is ambient obstruction flat, would indicate a critical point, tells us that this tensor is something worth investigating. Okay, so that's my brief kind of spiel on why we want to look at the ambient obstruction tensor, why it is cool or interesting. But let's look more at the ambient obstruction tensor itself to see why we might care. It has an explicit representation. That's pretty nice. But then we look at the explicit representation and we see that it is not nice. I mean, for one thing, we have this Schouten tensor, we have our scalar curvature term here and Ricci, and so it's really combining a lot of different aspects and measures of curvature in a nice way. But then we get this ambiguous polynomial natural tensor of order n-1 that's just tacked on at the end. We'll see in dimension 4 this plays out pretty reasonably, but in dimension 6, 8, 10, again, it's only even n. But for higher dimensions, it is not super nice. Okay, so it's vaguely interesting, not super nice. how do we reconcile these two things? Why is it even worth studying if it's this gross? Well, the ambient obstruction tensor, when considered for its properties, is actually a really nice tensor. So a few of its properties: it is trace-free, it is divergence-free, and it's conformally invariant of weight 2 minus n. Now, I say conformally invariant of weight 2 minus n. What that means is that a general tensor Q is invariant of weight W if, when I look at the conformal mapping by rho squared, Q, or when I change, when I change the metric by rho squared, my tensor gets changed by rho to the W. Okay, so that weight for my ambient obstruction tensor is just 2 minus n. Okay, this is a nice property. It's something that I think will prove useful in further studies. For now, we're just going to kind of black box it and call it conformally nice. Okay, so the ambient obstruction tensor is trace-free, divergence-free, and broadly conformally nice. Okay, useful property, but it won't really come up a whole lot in today's talk. Okay, now, one sort of confusing thing is that I like to think of the ambient obstruction tensor as one individual thing, but it is really much better to think of it as a family of tensors that all share these properties, okay, for every single dimension, right? Or every single even dimension greater than or equal to 4. For example, the Bach tensor is the family member, or is the ambient obstruction tensor for n equals 4. Each property, or each family member, has these properties in dimension n, but these properties are not guaranteed outside of that dimension. We'll talk more about this nuance when we look specifically at the Bach tensor and how this plays out there. But for each ambient obstruction tensor for dimension n, it is trace-free, it is divergence-free, and it is conformally nice. Okay, now, these two properties might look familiar, but before we look at using those two, let's look at how we would define an ambient obstruction flow and solitons. Okay, so an ambient obstruction flow, we're going to look at a smooth matrix H on a compact manifold of even dimension n greater than or equal to 4. Why? If our dimension's not right, the ambient obstruction tensor is not defined. Okay, and we're looking at a compact manifold to make things a little bit nicer. Okay, the ambient obstruction flow is given in general by this differential equation here on the left. I'll wait for my screen to catch up. There we go. Okay, now we see that it's the ambient obstruction tensor plus this scalar curvature term, which includes this constant c sub n based on the dimension that we're in. Why do we include that? Well, this term is included essentially to counteract that conformal niceness. The conformal niceness gets a little bit gross when you start to flow it over time. And Bio and Hellewell show in their papers that with this term, we're actually able to prove short time existence and uniqueness for this flow in general with this added term. Now, looking at solitons for the first time, no one's ever really considered them, so I want to look at the nicest case possible, which is why I'm going to focus on looking at only homogeneous manifolds. Now, if you recall way back to the beginning of the first part of this talk, you'll recall that homogeneous manifolds all have constant scalar curvature, meaning since this guy is constant, my derivative here goes to 0, this whole term goes to 0, so I'm just left with my flow being defined by changing the metric over time is equal to just the ambient obstruction tensor. So what I'm doing is I'm modifying my setting so that my flow is more manageable. And by doing this, we'll see that it has consequences when we're looking at solitons that make what we're doing feasible. Now, I do have some results that involve this term on a general manifold, but we're not having to force homogeneity on anything. But again, for this talk, if we limit ourselves to the homogeneous case, then our flow is defined thusly. Okay. Now, in general, for a general manifold, again, I have this whole term. In general, this whole term is my Q from the previous part. Okay, meaning that when I'm looking at solitons, my general solitons and consequently my gradient solitons look like this, where I've taken my Q, or I've taken this combination of terms, and I plug it in where Q was standing in part 1. The same exact definitions are true. I'm just considering this very complex Q. Okay, so in general, this is what a soliton would look like. It would be a metric G that satisfies these equations. However, we're only focused on the homogeneous case. In the homogeneous case, and this is really what we care about, in the homogeneous case, because Q is just given by my ambient obstruction tensor, again, because this term has gone to 0, when I plug Q in, I'm only having to plug in my ambient obstruction tensor. Okay, I'm only having to deal with that one single term because I have picked a nicer type of manifold to deal with. It limits the scope of my results, but it gives me a much nicer setting to do work in. Okay, broadly speaking, I think that this is one really helpful way to look at working in differential geometry, is how can I focus and pare down my study so that I am dealing with the nicest things, so that later, once I have results here, I can expand those back out. And that's one method, that's one approach, and that's the approach that I took when looking at ambient obstruction solitons. And as the study continues, we will open it up to a broader class of manifolds. But for now, we're sticking in the homogeneous case. Now, if you recall back to like 2 slides ago, we looked at the ambient obstruction tensor being trace-free and divergence-free. If you think back to part 1 of the talk, we saw that we had this result. If Q is divergence-free and trace-free, then our manifold must be Q flat. Okay, so let's put these two things kind of together into a result here. Let me make sure there's nothing else I need to say. Great. So a corollary to my lemma from part 1 is as follows. Let M be an n-dimensional compact ambient obstruction soliton with constant scalar curvature. So we know that we are dealing with an ambient obstruction soliton, and we know that it has constant scalar curvature. Okay. Now, one thing to note is a little bit of playing around here. In the previous slide, we looked at the homogeneous case. This is a sub-case of having constant scalar curvature. Non-homogeneous manifolds can have constant scalar curvature. But this was the only thing that we needed in order to get these kind of more refined flows. So for this corollary, to keep it as useful as possible, I'm going to look at that slightly more broad case. So I have an n-dimensional compact ambient obstruction soliton with constant scalar curvature. Then I can conclude these 3 things. First, I know that the integral of norm squared of my Lie derivative is equal to 0. I know second that x is killing, and the x involved in my Lie derivative. And lastly, I know that my manifold is ambient obstruction flat. Okay. Lastly, I know that my manifold is ambient obstruction flat. So how are we going to prove this? well, I've kind of already foreshadowed how it's going to go, maybe. First, we're going to see that since M has constant scalar curvature, we know that our flow is given by this differential equation here, where Q is equal to just script O. Okay. It's just equal to my ambient obstruction tensor. Using the properties of the ambient obstruction tensor, I know that it is divergence-free and it is trace-free. So my conclusions follow directly from lemma 1. All three of these things now apply to the ambient obstruction tensor very, very quickly. Let's look at this process kind of more pictorially to see how this plays out. So the methodology of how I'm going to approach proving things for the ambient obstruction tensor to kind of get around how gross the actual tensor is and start to use the properties that the ambient obstruction tensor gives me. The way I'm going to do this is I'm going to find a theorem for a general tensor. So in our case, I proved that for a divergence-free trace-free tensor Q, any compact Q soliton is Q flat. Then I'm going to find a specific corollary for the ambient obstruction tensor. That is, any compact ambient obstruction soliton with constant scalar curvature is O flat. Now, one thing to note here is that I did have to concede and force my manifold to have, or my soliton to have constant scalar curvature. In order to use the lemma, I had to adjust my settings so that it was feasible to use the lemma that I had proved in general. Okay. So this gives me two kind of conclusions. First, it points to the fact that all compact homogeneous ambient obstruction solitons are ambient obstruction flat. Why? Well, okay, this is just a specificity on the fact that since I have constant scalar curvature and all homogeneous manifolds have constant scalar curvature, this then very quickly follows as maybe like a corollary to a corollary, if you will. Okay. The next thing that follows is actually an established theorem from Ho, which says that any compact Bach soliton with constant scalar curvature is Bach flat. Okay? And this theorem was established in 2018 in dimension 4. Okay, so the way that I approached solving this problem, and I think kind of an interesting approach to solving problems in general, is to look and say, okay, if you've done this for this specific case, how can I extrapolate the patterns of what you have done, the moves that you have made, into a very, very general scenario? Okay, so I've taken this theorem, I've created this lemma, and this lemma does two things. First and foremost, it gives me a way to find results for the ambient obstruction tensor, which I care about. Not a lot of people do, admittedly, but it's cool. It's a promising tensor. It has an interesting backstory. We love it. Okay. The second thing that such a general lemma does is that it gives us a tool that can now be applied to any tensor that is divergence-free and trace-free, right? Let's say I take a tensor that is divergence-free and not trace-free. Well, part 2 of that lemma still applies, or part B rather, right? I'm now creating tools that can be applied for any Q soliton as long as Q fits those properties. Again, really carving out this fact that Q is just an empty box to hold some other tensor some other time. I'm going to give Q properties. Maybe I am motivated by wanting Q to have certain properties, or I care more about some properties than others. But if I'm able to do this for a general Q, I can find results for myself. I can create a tool for other different tensors, and that's going to allow me to look more broadly and consider different tensors down the road if I need to, and things like that. So that's really the methodology that we used, or that I used to find results for the ambient obstruction tensor. And what this did was it really helped me kind of get around the grossness that is the ambient obstruction tensor itself. But we'll see in part 3 of this talk in just a minute here that with the Bach tensor specifically, that grossness is very manageable, and it really makes a lot of sense to get into the weeds and to do the work, numerically speaking. Okay. So more on that in a minute. I'm going to take a break and jump back in afterwards.